Alright, here we have another circular motion problem, but we're really going to go all out on this one. We've got a car going around a banked turn of 10 degrees, and the static friction of the road is 0.3. If the radius of the turn is 10 meters, what is the maximum speed the car can have? So first, I kind of just want to draw this turn from overhead, just to make sure I know what's going on. Alright, so it's just taking a turn. Here goes the car. And we've got this radius r here of 10 meters and some velocity as it's driving there, v. Yeah. But, well, this picture, I can't see the fact that the turn is banked. I can't see the force of gravity, for example. This angle won't do for a free body diagram. I'm sure I need to see the bank of the angle of the bank of the turn. So here's the turn. It's like a ramp. And here's the car on the ramp. Okay. So I might as well make this my free body diagram. We've got mg pointed down, normal force pointed up, and friction will be pointing this way. Right, so now if you find that direction for friction strange at all, imagine what would happen if you took a turn really fast on ice. Well, you'd go sliding off in this direction, right? You'd fly off the side of the turn like that. Friction helps keep you on the turn. That's why it's pointing in that direction. Alright, so those are all of our forces. Now, remember that this is the direction of the center of the circle. Right? We are looking at is the back of the car as it turns into the screen and starts to turn toward the right. That's what we're viewing right now. So the center of the circle is straight this way somewhere. I'll call that the C direction. And I'll go ahead and call this the Y direction. Alright, so, let's see, that's theta right there, right? And so we need to do our Newton's second law equations. So the sum of the forces in the Y direction equals mass times acceleration in the Y direction. And the sum of the forces in the C direction equals mass times acceleration in the C direction. Now, when I see the acceleration in the C direction, I know I can write mv squared over r, as long as I set everything up right. AC is pointing toward the center of a circle, so it is v squared over r. Alright, so now we need to just literally list out all of our forces, and the sum of the forces in the y direction is equal to 0. Right? Because it's not accelerating down into the ground or up into the sky. So the sum of the forces in the y direction is 0. Now notice that I did not tilt my coordinate axis to match the ramp like I often do in ramp problems, because in this case it's very important that my c-axis points toward the center of the circle. Otherwise I won't be able to get my v squared over r in the equation over here. Since I did that, my other axis needs to be perpendicular, so that's what we're accustomed to. Alright, so as for the sum of the forces in the y direction, well, I see we have negative mg. That's the only easy one. The other ones have components in both directions. Alright, let's see if we can figure this out. There are my components for n, and here are my components for f. Alright, so we can show this angle ends up being theta here in f, and this angle ends up being theta there. Now you don't have to take my word or my pointy drawing's word for it. You can go ahead and geometrically confirm that. It's a pain. So there are my thetas. Okay, so here we left off with 0 equals negative mg here in the y direction, but it's plus the y component of n, which is n cosine theta, and then minus, look at the friction's y component, it's pointing down, so minus the y component of friction, which is going to be the friction times the sine of theta. Okay. Now over in the x direction, I was left off with mv squared over r, and it's equal to, well, in the x direction, I've got the friction, positive friction in the x direction is going to be friction times the cosine of theta, and then plus the x component of the normal force, which is going to be n sine of theta. Alright, now recall that friction is defined as normal force times the coefficient, so let's go ahead and substitute that in. mv squared over r is equal to normal force times mu cosine of theta plus n sine of theta. Over here I've got, I'm going to add mg over. mg is equal to n cosine of theta minus n times mu sine of theta. So I don't know n, and of course I don't know v, that's what we're looking for. I see over here though, the only unknown is n, so let's solve for n in this equation. I'm going to pull out n, and solve for it. Like so. And now that I know n, I can plug it in over here. So I get mv squared over r is equal to, so I'm going to go ahead and pull n out of this equation here before I plug it in. So n is mg over cosine of theta minus mu sine theta. So that's n times the mu cosine of theta plus sine theta. Now I see my masses cancel out on both sides, which is good, because we didn't know it. And I multiply over this r, take the square root, and I get that v is equal to r times mu cosine of theta plus sine of theta over the cosine of theta minus mu sine and the square root of all that. Those are necessary.